So, welcome all of you to the third lecture in the series of lectures on gravitation. So, what we have done so far is to revise the kinematical aspects and also the three laws of motion as enunciated by Newton. And after that, we also discussed conservation laws and two laws, in fact 3 laws, which are of utmost importance to us. They are conservation of momentum, conservation of energy, and conservation of angular momentum. We shall see that when we discuss planetary motion, the so-called Keplerian orbits and gravitation, all the 3 of them have a role to play. In fact, the famous second law of planetary motion is nothing but a statement of the conservation of angular momentum, which was realized once the gravitational law was formulated by Newton. We also discussed very qualitatively as to how large distances can be measured by making use of trigonometry. So, it is not that one needs a scale or an inch tape or any other measuring instrument and that we have to physically travel to determine the distances. We can also infer what the large distances are, such as the radius of the earth, assuming that it is a perfect sphere, or the distance between the earth and the moon, or the earth and the sun, so on and so forth. If we can invoke additional principles, both mathematical and physical. So, for example, we can make use of trigonometry and then measure one side and an angle and try to get either the distance or the ratios of the distances. So, I gave 2 examples, one of the measurement or the estimation of the radius of the earth by looking at the angle formed by the sun's rays at the same time at 2 different points. I also sort of hinted at how the other distances can be measured through parallax probably. So, today what I will do is I will illustrate that in a slightly greater detail as to how distances and ratios can be estimated, because this is fundamental, otherwise Kepler would not have been able to formulate his laws. We should remember that when we look at the celestial sphere, our eye cannot make a distinction between distances. All of them appear to be at the same distance because it is all on the sky. The sphere is defined there, and therefore we need these indirect techniques, and that is what I am going to discuss. So, basically today's lecture will cover a little bit more discussion on how distances can be estimated. More and more careful observations will give you better and better approximations, better and better values for distance. So, in the passing I will mention about the accuracy of the observations. After that, I will discuss Galilean law. The Galilean law is the law of freely falling body. Then we go to Kepler's laws, which refers to the heavenly bodies. We are going to combine the Galilean law and Kepler's laws with centripetal forces and then argue that it is a very rational thing to formulate the law of gravitation as Newton did. So, when I say it is rational, I do not mean that it is an easy thing or a trivial thing to do, because we should remember that when Newton worked on universal law of gravitation, he did not have the concept of force. He did not have the concept of momentum, so he had to introduce momentum, he had to introduce force, he had to introduce the law, and then he had to apply it to the law of gravitation. Even more importantly, Newton did not have the concept of action at a distance. All the forces that people knew were contact forces. Like for example, mass spring system, the spring is in contact with the mass. So, all forces were assumed because of the contact between 2 bodies. So, here was the first situation where Newton was trying to formulate a law where a force can be exerted even when the 2 bodies are not touching each other, they are not in contact with each other. So, if you read an authenticated biography of Newton, you will find fascinating discussions on these matters. So, what we are going to discuss is rational by hindsight, natural by hindsight, but it was quite revolutionary when Newton formulated. So when we come to astronomical observations, we should remember that the humankind has always been fascinated by the stars. I think it was Kant who said that there are two things that fill his heart with awe. One was the order of the celestial spheres in the sky, and another was the moral law within him. And this goes back to thousands of years, to Babylonians, Egyptians, Greek, Roman observations, Indians, and the Chinese. Probably the Mayans also did a large number of observations. We don't have much detail. So when we speak of the so-called astronomical observations and the formulation of laws, we should remember the data collected by all these civilizations spread over many, many centuries have had an important role to play. We should not forget that. So what I will now do is to illustrate to you how the ratio of the distance between the Earth and the Moon and the radius of the Earth can be estimated by looking at lunar eclipse. So this is one of the fascinating examples, and I think this example is due to Aristarchus, and let us see how we get about, and let me illustrate that in an easy fashion. So what we shall do is to assume that we have the Earth, which I am showing by the small sphere, and that the Moon is going in a circular orbit. There is no conflict in this, whether it is the Aristotelian viewpoint or Galilean viewpoint. All controversy was about whether the Earth is going around the Sun or the Sun is going around the Earth. Nobody doubted whether the Moon is going around the Earth or not. So what we shall do is we shall denote the distance between the Moon and the Earth by capital R. So this is Moon's orbit. So at this point we are making an assumption that the orbit of the Moon is circular. That is an important assumption. This assumption can be tested through various careful observations. In fact, if you look at the astronomical data, observations and also calculations, both by the Roman Greek school and also the Indian school, Aryabhatta or Bhaskara, they always gave the mean distance because they were aware of the fact that the distance changes, because by looking at the transit time between any two different angles on the celestial sphere, they knew that. But here we are not asking for a precise determination of the distance between the Earth and the Moon, but we are interested only in the what? Estimating the distance between the Earth and the Moon. So we are allowed to make a large number of approximations. Now in order to illustrate, I will magnify the size of the Earth. So I am going to bring it here and illustrate it here, and I will show the radius of the Earth to be RE. I will represent it by RE. Therefore, we have two scales here. One is the distance of the Moon from the Earth, which I am calling as R, and another is the radius of the Earth. So Earth Moon distance R, radius of the Earth RE. Remember, we already discussed how the radius of the Earth can be determined very accurately. It is about 6,400 kilometers, maybe about 20 kilometers less than that. We will never bother about that. So we know this, and what we want to do is to try to get a handle on the value of capital R. That is what we want to do. So now I am going to draw another picture, and what I am going to do is to look at the eclipse. There are two eclipses that take place. One is the lunar eclipse, when the Earth comes between the Sun and Moon, and we have the solar eclipse when the Moon comes between the Earth and the Sun. Here we are interested in lunar eclipse. So all of us know that lunar eclipse takes place on a full moon day, and a solar eclipse takes place on a new moon day, Purnima and Amavasya, that is when it takes place. So now let us ask what happens. So you have the earth here, and what we shall do is to assume that the sun is at a very, very large distance compared to the distance between the earth and the moon. That is what we shall assume. And we say that an eclipse is forming, we are observing an eclipse simply because the moon enters the earth's shadow. That is what is happening. So if the sun is very, very far away, then you know an object at infinity will produce parallel rays. So what is happening is that I am going to illustrate it schematically. So the sun is at infinity. So the two rays are coming here. So if you forget about the finite distance between the earth and the sun, we will come to that later. And if you forget about the size of the sun itself, the angular size of the sun, because that can cause umbra and penumbra, we will forget about that also. If you forget about both of them, then what you have is two parallel rays, and the shadow is cast here. Basically, the shadow is of an infinite extent, and the shadow is not going to diverge. If you have a finite size, the shadow is going to diverge as you go farther and farther away. So irrespective of where the moon is going to be in this shadow region. This is the time for the shadow region. And what is this distance? This distance is nothing but the diameter of the earth, which is 2re. This distance is nothing but the diameter of the earth, which is 2re. So all that I need now is to know how long it takes for an eclipse to start and an eclipse to end. So we have to be a little bit careful about that, because the moon has a fairly large angular size. The full moon appears quite big actually, especially when it is rising. So we can fix the center of the moon, for instance, or the periphery of the moon. That is what we are going to fix. Is that okay? So find out the time taken. So this is nothing but the duration of the eclipse. So what are we saying? We are going to approximate this true orbit. So the moon's orbit is something like this. We will not worry about the difference between the circular orbit and this perpendicular line. So basically we are saying that the moon takes a certain transit time. So t transit through the shadow, and the distance covered is 2re. So this is the data that we have. Very simple. Now let me write down the figure again now. Here is the earth, here is the moon's orbit, and here is the distance r. Now if I assume that the moon is moving with a constant angular velocity, now what is the total distance covered? The total distance covered is 2 pi r, and I know the period of the moon, which is close to 30 days. So the moon requires 30 days to cover a distance of 2 pi r. So for 2 pi r, you have 30 days, and for a distance of 2re, you have the transit time. You have the transit time. Now if you assume that the moon is moving with a uniform angular velocity and therefore with a uniform speed, you get the speed from this, because you know the radius of the earth. Plug it back and you get the distance between the earth and the moon. Or if you think that, okay, I don't know the radius of the earth very well, then you can look at the ratio r by re. That can be uniquely determined because the two periods are known. It is nothing but proportional to the ratio of the two periods. So this is nothing but t over the transit time, whatever I wrote as t transit. This is the duration of the eclipse. This was the genius of Aristarchus. Now if you work out this distance, it turns out to be roughly 60. Today, there are extraordinarily precise measurements, actually measurements, not just observations of the distance between the Earth and the Moon through lasers. You send a laser beam and you ask for the time for the laser beam to go, hit the Moon's surface, get reflected and come back. And you know, light travels with an enormous speed, 300,000 kilometers per second. So we can estimate the distance very precisely, and this number 60 is remarkably close to whatever we have from modern day observations. Now all that you have to do is to plug this RE equal to 6400 kilometers, and this gives you an idea of what? This gives you an idea of the distance between the Earth and the Moon. Now if you are a little bit smarter and more careful, you can see that this observation can also give you an idea of the size of the Moon, because you can ask how long does it take for the front edge of the Moon and the right edge of the Moon to come. The eclipse starts, you know, and then it, so if there is the eclipse that is going to start and it is going to end, I said that we have to look at the center. You can also look at the distance between the two edges, so that will give an idea of the radius of the Moon, and that in fact will tell us that the Moon is much smaller than the Earth. Otherwise, it is extraordinarily difficult to decide whether Moon is bigger than the Earth or the Earth is bigger than the Moon, but this measurement should be able to tell us. So we see, if we assume, and that is a perfectly reasonable assumption to make, that whatever we find at our terrestrial scale, sum of three angles of a triangle is 180 degrees, two parallel lines shall never meet, etc., etc., all the theorems of geometry, they also hold at the large scale over lakhs of kilometers. If you assume that, trigonometry and these observations will tell us how to estimate such large distances. So now we can safely say that we know the distance between the Earth and the Moon, because somebody used another principle to determine the radius of the Earth. The important point that you have to know here is that not only can we estimate, in fact, we can make it more and more precise. For example, around 4th century or the 5th century AD, the period of the Moon was known to a precision of 1 minute. We are speaking of 1 minute. Here I wrote approximately 30 days. It's actually 29 point something something. So you can bring it down to hours. You can in fact bring it down to minutes by repeated observations. So once you know the period more and more accurately, and once you are able to measure the radius of the Earth more and more accurately, these distance estimates also become better and better. So astronomical observations are of great interest. Now I will illustrate to you how we can actually estimate the distance between the Earth and the Sun. In fact, distance between the Earth and any planet. The idea is to look at transit times. So there are things called occultation. Moon, for example, you ask, Venus, for example, you ask, how long does it take for Venus to go from one edge of the Sun to the other edge of the Sun? It's a circular disk. And if you know the distance between the Earth and the Venus, then you can immediately estimate what the radius or the diameter of the Sun is. So this is how we intelligently estimate. So here what we shall do is not look at either the lunar eclipse or the solar eclipse. Let us look at the half moon. So this is the 8th day roughly, what we call Ashtami, which is a very important day for many religious purposes. So when does it happen? The new moon happens when the moon is directly in between, apart from some corrections, because it is not exactly in the same plane, between the Earth and the Sun. And the full moon happens when the moon is directly in the other side. The Earth is between the Earth and the Sun. But half moon occurs. So to show it schematically, you have the Sun here, you have the Earth here, and you have the moon here. Please don't be misled by this diagram, because this diagram gives you an impression that moon is farther away than the sun. This is not to scale. So this is your Ashtami, the 8th day. Now what I will do, all that I need to do is to measure one of these angles. All that I know is to know one of these angles. I know this distance already, and if I know the other angle, I will leave it as simple exercise for you people. You can find out yes, the distance between the earth and the sun. That is what you can do. So what are we doing? So let us look at tan theta. Tan theta is Rs by R, and tan theta can be approximated by theta, because theta is going to be very, very small. So in the first step, you estimate the ratio of Rs by R. This is the distance between the earth and the moon. This is the distance between the earth and the sun. And then if you know, or if you assume that you know the distance between the earth and the moon, you know the distance between the earth and the sun. There is nothing very specific about the sun. You can put Venus, you can put Mercury, you can assume that they are all moving in circular orbits, and in this particular manner, you should be able to estimate all distances, and that is what the great astronomers did. So when we are speaking of Kepler's law, what the astronomers did, starting from the time of Ptolemy or even earlier, was to observe the night sky with great patience, with great persistence, note the reading, create elaborate tables, and of course you want a table of trigonometric functions. So they calculated sines and causes and tans to enormous accuracy. In that process, they in fact even developed series expansions, etc., etc. Even though calculus was not formally invented, they were able to do a whole lot of things. Of course, they were doing spherical trigonometry, so-called, but it doesn't matter to us very much. So by the time of Kepler, after the great observations of Copernicus and Tycho Brahe, we were in possession of an enormously rich table of all astronomical data. That is very, very important. And one more important piece of information is that there was absolutely no evidence that the fixed stars, which are far, far away, were moving with respect to the earth. So the general assumption was that the earth is at the center of the universe, and then there is this largest sphere where the fixed stars are, which is at rest with respect to the earth, and then there are all these other spheres in which the planets and the sun was going. It was a completely rational picture. So that is the picture that the astronomers had, and now we have to see as to what the observations had to say. So now let me come back to this slide for a few minutes, because I have to show you a few more things, and then let us get back to a little bit more of calculation. So in this slide, what I have done is to put in some numbers. I told you already, Earth's radius is 6400 kilometers. Period of the moon is about 30 days. Okay. This approximate sign should have been everywhere, so please read it as approximate sign. Duration of the eclipse is about 3 hours. We know that. So 3 hours is the time taken to cover a distance of twice the radius of the earth, diameter of the earth. That is the statement that we are making. That immediately tells us that the distance between the earth and the moon is about 60 times the radius of the earth. 60 into 6400. So 10 cubed is about 10 to the power of 4 kilometers, with a number of the order of 2 or 3 or whatever. That is the kind of number that we are giving. At this point, it is good to ask how these observations were made. So for example, if you go to Jaipur or to Jantar Mantar in Delhi, or just behind our IIT in Delhi, there is this Lal Bahadur Shastri Sanskrit University. If you go there, they have built observatories in order to observe the sky. They are all concrete structures, and you will see sundials, then you will see parabolic surfaces with markings, and you basically, and there are gnomes. Gnomes are essentially sticks, and you measure the length of the shadows cast by the sun, etc., etc., to find out, for example, exactly when the noon is, when the moon rises, what is the speed at which, angular speed at which the heavenly objects are traversing and all that. So this is how people measured all angles and all periods. Period measurement is a little bit more tricky because they did not have accurate watches. So they had probably hourglasses. So you put some sand, or you take a water with pot with water, and the water keeps trickling down drop by drop, and to count the number of drops, so on and so forth. So one may think that it is impossible to get something like a period of the moon with such a great accuracy with such observations, because they certainly did not have a clock which measured time with a resolution of 1 minute, although people use words like nimesh and all that. The answer to that again is in a principle. So remember, when you perform an experiment with your simple pendulum, your least count may be a minute, but then you are not going to measure the period of a pendulum with one oscillation. You are going to do a large number of oscillations, let us say 10, 15, etc., etc. So if you take the initial reading and if you take the final reading, and let us say that your pendulum is pivoted very beautifully so that there is very little friction, and you are able to do 50 oscillations, let us say, or 100 oscillations, then the least count does not add up with every oscillation, because you are going to make an initial time and the final time, and then you are going to calculate the period, but the uncertainty is only given by the least count, at most by twice the least count, but that least count gets divided by the number of oscillations. So that way you are invoking a new principle. In fact, that was the great contribution of Galileo when he looked at the oscillating, I think one of the lanterns in St. Peter's church in Rome, and he thought it was executing a periodic motion. That is what you do. Therefore, you are able to beat a so-called physical hurdle by invoking a principle. What is that? That it is oscillating with a perfect period. So even here, even if your clock itself does not have a very great accuracy, let us say it has an accuracy of 1 minute or even 2 minutes, but if you observe the period over a large number, so you don't ask what is the time taken by the moon to complete 1 full revolution, but 10 full revolutions, 100 full revolutions, then this least count does not become a limitation. That is exactly what they did, and they were able to fix it as 1 minute, up to about a minute. So there are many people who get confused and say, oh, they did not have any accurate clock. They simply made all kinds of statements. That is not correct. Without realizing, or perhaps with realization, they were actually more likely with realization, they were able to beat the so-called physical hurdle. That is something that we should always remember. And that is how physics always grows. There is something called a diffraction limit, which people are able to overcome through some other physical principle. But the most important point in all these observations was that they were all naked eye measurements. They were all naked eye measurements. So it could not have been able to satisfy the demands of precision and accuracy that we make today, but it is remarkable that they were able to make so many observations. So then comes Galileo. Galileo not only gave us the first law and the law of falling body, Galileo did something remarkable in the field of observation. He made the first telescope. He observed people, using these lenses or double lenses to read or magnify, and he thought, instead of directing it towards the earth or some distant object on the earth, let me direct towards the sky. And when he did that, he discovered many, many remarkable things. One of the most remarkable things was the moons of Jupiter, which are not visible to the naked eye. So he was able to discover them. He was able to decide decisively that the markings, the beauty spots on the moon, are because of the craters. So here is a original piece of Galileo. It is in Museo Galileo somewhere in Italy. Museo is museum with a magnification of 10, and that completely revolutionized astronomical observation. After that, there was no going back. They were reflecting telescopes based on reflection. People built parabolic mirrors. If I remember correctly, Newton actually built the first reflecting telescope. Now you make the aperture larger and larger, the gathering area larger and larger, and you are able to make measurements. So that is something that we have to remember. So what we have at our disposal is very, very accurate tables. Now what I will do is, I will digress. What I will do is, I will not continue to discuss Keplerian law, but I will discuss something remarkable called the equivalence principle. Now the word equivalence principle was coined by Einstein almost 500 years after Galileo made the observation. Galileo himself did not call it equivalence principle. Newton implicitly used it everywhere, and after that every physicist, every mathematical physicist who worked on planetary motion from Newton to Poincaré, everyone used it, but nobody was able to realize that it is a fundamental principle. And this equivalence principle is what is embedded in Galilean law of a freely falling body. I want to discuss that. Then I want to go back to Kepler's laws, which were formulated based on the planetary observations, especially of Copernicus and Tycho Brahe. And then I will combine the two and I will try to show you how gravitation is something very causes a very pleasing description, unified description of both terrestrial and celestial phenomena. Okay, actually I have gone to planetary motion. So what I should do is I should go back here and start discussing equivalence principle. So let us get into that. All of you have used this without paying much attention perhaps to the mystery of the whole thing. So in order to formulate equivalence principle, let us start with Newton's equation, second law of motion, and let me illustrate what is happening. So Mr. Newton tells us that the rate of change of momentum of a body is equal to the applied force. We had a fairly long discussion on the nature of this applied force. So let me write a few examples again. Redundancy is extraordinarily good when we are learning a subject. There is no harm in repeating. For example, I will write minus Kr. This is hook. I will write Q into V cross B. This is Lorentz. Motion of a particle in a magnetic field. I will write QE, and this is Coulomb. In an electric field, this is the force which is experienced. I can write a whole lot of things. For example, there is a frictional force which is proportional to velocity, minus K mod V. So when I am writing all these things, if you look at the right hand side, there are different applied forces which are characterized by different properties, and there are two properties essentially. The first property is the sensitivity to distance or velocity. For example, Hooke's law is sensitive to the distance from the equilibrium position, but it is not sensitive to the velocity. Whereas, if you have a uniform magnetic field, for example, the Lorentz force is sensitive to the velocity and not where you are located. Of course, if your magnetic field also changes with position, if it is an inhomogeneous magnetic field, then this force is sensitive to both velocity and the position. Same thing with electric field. It is sensitive to where you are located. The electric field in general takes with this one. Here you are sensitive to velocity. Here you are not sensitive to position. That is one property. The other properties are various strengths. So strictly speaking, I should put a K here and I should put a K prime here because they are two different things. One is the sensitivity. How does it change with the distance? How does it change with velocity? Does it decrease? Does it increase? If it decreases, at what rate does it change? That is the question that we are asking. The second one is, what is the strength? Now the strength is characterized by what I call Q, K, K prime, and these are parameters. These are the strengths. For the same magnetic field or for the same electric field, if you put different bodies of different charges, they respond differently. So increase the charge by a factor of 2, the force increases by a factor of 2. Decrease the charge by 50%, the force decreases by 50%, so on and so forth. So, distance is a property of the field, whatever the thing is, this is a property of the object. How do you respond to that field? K, K prime, charge, etc., etc. It's a property of the test body. Therefore, the response to an applied force depends on your own characteristic, like your charge or like your resistance to motion, etc., etc., like the spring constant, so on and so forth. So, this is very, very important. Now, what we shall do is to look at the left hand side of the thing. Left hand side is universal. So, my momentum is nothing but mass into velocity. That is what I have. So, there are two things. If I therefore write m equal to dv by dt into, let us say, some k, this is also a property of the test body, into some function of r, v, you can make it t. That is what I am doing. So, if it is an electric field, this will be the electric field, then this will be the charge. If there is a magnetic field, this will be V cross B, and this will again be the charge, so on and so forth. So, that is what I have. Now, you see there is a competition. My particle has a charge, my body has a charge, which says, oh, please interact with the force. Let your response be greater and greater. Then it has a mass which says, no, 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 resist the action of the force. So, this is inertia. This is resistance to motion, and this is the charge. So, when a person gets very emotional, we say the person was charged, because the person speaks with a great force. That is the statement that we make, and it is not accidental. Whereas, if there is no great enthusiasm, we say the person has a great inertia. So, every object comes with an inertia which is characterized by its mass, and then you have the charge corresponding to the interaction. Your spring constant is the charge for Hooke's law. Your electric charge is the charge for your, for instance, for your Coulomb law, so on and so forth. And the final response depends on this charge by inertia, K by M. And that is the reason why Newton called this as the inertia. Greater the mass, greater the inertia, and that is the reason why many times you say, if you have a very, very massive body, take it to be infinite and don't worry about its motion. That is what you do when you look at the motion of the earth around the sun, because the sun is so very heavy compared to the earth, you don't have to worry about its motion. It has momentum, but very little velocity. That is what we are going to do. So, by the same token, now let me look at the freely falling body. So, there is this very famous experiment. So, this is your Leaning Tower of Pisa. So, this is where Galileo was standing, let us say, and it is some height h. So, he dropped objects. Of course, when you do an experiment like this, you should minimize the contribution coming from air's viscosity, etc., etc. So, you have to take fairly heavy objects. So, let us assume that we take balls of lead, iron, heavy metals, stone, etc., etc., of different masses. So, imagine that you have a graduating scale here, and you start measuring the rate at which they fall. Now, what is it that Galileo observed? When we say freely falling body, what do we mean by that? All of them are released from rest. All of them are released from rest. So, you can imagine 3 of you, 4 of you, you climb up the Tower of Pisa, or you climb up a high building in your apartment complex or whatever. Find a time when there is nobody around. Each of you holds different blocks, iron, stone, whatever, heavy objects on which the resistance from the air is negligible, and you drop them. And if you were to carefully observe, what is it that you would find? That they will all move together at any given time. If they are released simultaneously, at any given time, both of them will be together, and eventually they will reach the earth at the same time. So, with respect to lead, iron is at rest. With respect to iron, lead is at rest. And of course, with respect to us, both of them are moving together. They have been released from rest. There is one more law. It is not just that they are moving together. And what is that? Let me write it in the next sheet of paper. So, all bodies are at rest with respect to each other So, we should remember freely falling bodies released together. There should be no confusion. Number one. Number two, they have uniform acceleration. Irrespective of their mass. That is what we have. So, the first one is a qualitative statement that they are at rest with respect to each other. The second one is more quantitative. So, A is independent of the body. Size, shape, mass, it is independent of everything, and we know what this is. G, acceleration due to gravity. That is what we have. Now, please try to combine this observation with what Mr. Newton is saying. Of course, when Galileo discovered his law of freely falling body, there was no formulation of Newton's law, but we are not under any obligation to follow the historical sequence in understanding forces. Newton says that m into a, acceleration, is applied force. That is what I have. Therefore, my acceleration should be force applied divided by the mass. That is what I should have. Now, I will become a little bit fussy, and I will remind myself that this mass is not any ordinary mass, it is inertia. So, there are two concepts of mass. We have to understand that. One concept is the quantity of matter contained in an object. So, imagine that it is made up of identical atoms. So, I will simply count the number of atoms, and I will simply say that is the mass. And if there is another body of different atoms, I will ask, how many atoms of the other body should be there in order to make one atom of this, mass wise, the quantity wise. So, I can do that. So, the point is that the acceleration should be inversely proportional to the mass. That is very important, and this law cannot be violated. So, what is the word that we use in Indian languages, for example, for gravitation? Gurutvakarshan. There is an attraction. There is a force that binds us all to the earth. So, just as a body should have charge in order to respond to electric field, it should have some other property in order to respond to, it should be connected to the spring in order to respond to the Hooke's law, so on and so forth. The body should have a property which responds to the gravitational field. For example, if a body does not have a charge, it will not respond to the electrostatic field. A neutral object, take a neutron and put it in a electric field, nothing will happen. Take a neutral object, put it in an electric field, nothing will happen. It is not going to accelerate. That is what is going to happen. Therefore, we should ask, what is the charge, quote unquote charge, that is strength. What is that property of the body? This charge is called gravitational mass. It should actually be called gravitational charge, like electric charge, some other charge, but people call it gravitational mass. That is what it is called. Now, the beauty of freely falling body is that the force, I don't know what it is, exerted by the earth on the bodies is independent of their mass. So, what do I mean by that? I am going to write MA is equal to M into some function. That is what I am writing. Earlier I wrote Q into some function, K into some function, K prime into some function. That is what I am going to write. I cancel them, and this is extraordinarily remarkable. It is remarkable in two senses. One is that the inertia is counterbalanced by its charge. So, it has two hats. As an inertia, it opposes. As a gravitational charge, it supports, and they perfectly balance each other, number one. Number two, we can say that a particle may have a charge, it may not have a charge. A particle may have a magnetic moment, it may not have a magnetic moment. But at least in Newtonian physics, you cannot think of a body without mass. In fact, a body is characterized by its mass. Without mass, nothing is going to happen. That means the earth, our mother earth, is going to act on everybody because everybody has mass. So, there is a universality. Of earth's pull on the bodies. Newton noticed this universality in his formulation of gravitation, but Einstein not only noticed the universality, he found that this is a very profound principle. In fact, this is what allowed him to formulate the famous general theory of relativity. So, please remember that Galilean law of freely falling bodies has given this principle, equivalence principle, that earth attracts all bodies towards it with the same acceleration. The forces differ actually, but then the inertia and the quote unquote gravitational charge cancel each other. That is very, very important for us to know. And what about a piece of paper, for example? Even that obeys the same law. You can create something like a Torricellian vacuum, evacuate all the air, everything, and if you drop a piece of paper, that will also fall with the same acceleration. There is nothing to stop it. So, this is the one of the most important inputs, and this is what I showed in this slide as the equivalence principle. Now, let me come back to astronomical observation. So, basically I am going from, I am toggling between terrestrial to celestial. In plain English, earth, sky. That is what we mean. So, now let me go back to astronomical observations and let us write down what Kepler did. And here we have many lessons to learn, and let us proceed slowly. So, before I proceed, let us imagine that somebody has a long thread. So, here is a person who is standing, there is a long thread, and then this is moving in a circular motion of radius r. So it is executing a motion. All of us know how it is. X equal to r cos omega t, y equal to r sin omega t. I will write it. So this is the kind of example that you write, and you immediately discovered this is nothing but an equation of a circle. So what do? I will observe that x squared plus y squared equal to r squared. So I declare that it is a circular motion. Now what happens? This equation can become a little bit more complicated simply because I did not choose a simple coordinate system. I did not choose this center, but I will choose this center. This as the origin. Now what will happen? Now what will happen is I will write some x minus x naught equal to r cos omega t, because I have simply shifted my origin. Y minus y naught equal to r sin omega t. Now if I open it up, I am going to get a very complicated equation between x and this as a function of time. So let me open it up. Let us not be lazy. So what will it be? For example, I will write x squared minus is equal to 2x x naught plus r squared cos squared omega t. That is what I am going to get, plus x naught squared minus x naught squared. Simply y squared is equal to similarly 2y y naught plus r squared sin squared omega t minus y naught squared. So if you choose a wrong coordinate system, you will plot x as a function of time, y as a function of time. So I will put a square root here, I will put a square root here, I will put a square root here, I will put a square root here. It doesn't look like an equation of motion for a circle. It looks very complicated. You see that, right? But it is a circle. So in your geometry course, in your 11th standard, 12th standard, you actually devise method of finding out whether the trajectory is a circle or not, independent of the coordinate system. Is it a parabola? It is an ellipse. So these are the exercises that you are going to do, and this is what we have. Now I will complicate your life a little bit more. Imagine that there is a merry-go-round and it is going round and round with uniform velocity, and I am not observing that first of all from the center of that central pole where the merry-go-round is. I am standing somewhere outside, and standing somewhere outside corresponds to this x naught and y naught. Not only that, I am myself running. I am on a bicycle which is moving along a certain direction. Now what will happen? With respect to me, this will be something like x minus x naught minus vt, because I am moving with a constant velocity. Now if I open up, now you can easily see that not only I will have a cos squared omega t term, there will be vt, v squared, t squared, so on and so forth. Now I have got a very, very complicated equation. But the fact is, although the child who is sitting on a horse in the merry-go-round is going in a circular orbit, for us it will look very complicated. In fact, the orbit does not even appear to be open, because with respect to me, this student, this child who is sitting in a merry-go-round is executing a very complicated motion. What I am doing is to superpose my own motion. Of course, we don't know whether the whole merry-go-round system is moving with respect to the person outside, or the person outside is moving with respect to the merry-go-round. That's a different matter altogether. Luckily here, the earth is the standard for us. But the big question that we can ask is, whenever we make an observation of positions and angles with respect to time, what is the simplest description? And this is a very, very important question. So when we speak of a simplest description, we are asking what is the simplest frame of reference? How do I choose the origin of my coordinate system? That may require my moving myself to a new origin, reorienting myself, or perhaps even giving myself a certain velocity. These are the three things that I have to do, and that is what I have illustrated. Now it was the genius of Kepler that he could make sense out of the planetary observations through a trick. The trick was that Kepler discovered that the simplest description is when we make a shift to rest frame of the sun. And this is what normally people call the heliocentric model of the planetary system. But we should remember, this is not going to justify heliocentric model because we are only making a kinematical transformation. But this strongly suggests that it is more likely, or certainly it is a better description, if you assume that the planets are going around the sun rather than around the earth. So we have almost run out of time. So what I will do is I will stop at this particular point, and in the next class I will start with a careful enunciation of the Keplerian laws, which are some of the most important laws which are written in the history of humanity, and then we will show how Newton was able to exploit that and formulate his law of universal gravitation. The word that you should remember is universal. So let me stop here. Bye.